Alright, so let's get started working on the free, I guess. So let me just bring that up right there. I'm gonna need to pick this up and I'm gonna go down here. Do something like, actually we don't need to do that. I'm gonna just do this. I'll call this free and actually close that. This is the mem alignment, I think. And that's pretty much all we need. Actually, just gonna get this here, do something like so. Yeah, let's call this context. And I guess we can change this to free. And I think we are going to need to pass it a pointer. So let's just split the memory field or memory param to memory dot pointer and memory dot length. Sure. For now, we are not doing any return address tracking, nor are we needing the alignment. And actually, we might want to at least pass the alignment. Alignment, yeah, sure. It's just so that we can do something with it if we so decide to do. But in a bit, not just yet. So alignment, which would be a stud mem alignment thingy. Just gonna see what that is. So it just chooses the number of bits. And what is this order? Oh, okay, fine. That's just to compare them. Right, so where would we need to use this alignment? I think we'd need to use it to this. For now, we are aligning to min block size, but that surely is not enough in all cases. So we might want to align to this alignment instead. But for now, let's just ignore it and move on. Right, so let's get started on this free function here. Not sure this needs to be public. Yeah. So let's make a public function called free that takes self, which would be a pointer to this. Or we actually defined a self before, so let's just use that. So self would be a pointer to self, and then we'll take the pointer, which would be a, I guess, many item pointer to U8, and a length, which would be a U64. And this would do nothing. Yeah, we'll see. So this one does nothing, this one does nothing, so I'll just get rid of this. Okay, that sounds pretty good. So I guess let's get started on this. So first of all, we do have a pointer. We are going to need to figure out, and we have a length, also very important. So first of all, let's take a look at allocate. We figured out the length, and then we've gotten the matching bucket for that length. Right, so I'm pretty much sure we are going to need to do the same thing here. Once we once we get the length, the matching bucket, we are going to use the pointer to get the node index from the bucket. So I think that's self pointer or node from pointer, and it takes the bucket, so matching bucket, and it takes the pointer as int, and that would be this. Right, so now that we have our node index and we have our matching bucket, we are going to, so what is the game plan here? The game plan is to go from our current order all the way up to the highest order, the one that contains the full memory, and along the way, every time, so hold on, let me just try to draw that. So let's put ourselves in our usual example here. There we go. So this one would be order 2, this one is 1, this one is 0, right? So let's assume that this is the node we are trying to free. So what we are going to do is we are going to first of all check. So we have currently bucket ID is 0 and node ID is 1. This one is 1. So we are going to check the body of this node. This would be this one here. If it's free, so basically we are checking that in node state the bit is 1. Yeah, if the bit is 1, that means one child is used. And since we know that we are the child that is used, we know for sure that our body is free. So if the bit in node state is 1, we know that our body is free, so we combine the two and we move up one level, right? And so now we have, so this one is step 1. Here at step 2 will be at bucket 1, and node would be the parent node of this one. So that would be node 0, right? So step 2, whoops, that's a 2x square. Right, so now we are in this bucket here. So bucket 1 with node 0, we check its body. So this one here was also used since our child is used, and this one is not used. So we check its node state. It should still be a 1. If it's the case, then we remove it from its free list and we go to step 3. And in step 3, we'll be at bucket 2, and we'll move to the parent node of this node here. So that would be node 0 still. And since we are at the root, we basically can do no further checks. So we exit this loop here, and we insert a free block that has the size given by, or a cell size given by the bucket number we've reached. So this one would be, if we exit from here, this one would be 2, and we know that the size of this bucket order of 2 would be the full memory. So we just basically put back the full memory in the free list. If at any point here during our checks, we found that the node state is not 1. So basically, we cannot recombine the two bodies. We exit from there. And I think we'd do pretty much the same. So we'd still insert one cell or one node into the free list of that bucket ID, that order ID that we've reached within our checks. So to summarize here, this loop here removes the corresponding bodies from their free lists if they are free, or if they are unused, and then moves us up one bucket and to the parent node, which would be the two bodies combined. And we do the check recursively until we find that either we've reached the root order or we haven't found a body to recombine. And in that case, we just exit, we put back the free block that we've found, that we've recombined so far. Okay, that sounds pretty convincing to me. So, we are going to need a variable, and I'll call that bucket, and it's going to start at matching bucket. Yes, and then we are going to go while bucket is less than max order. Sure. So let's think about this now. We want to check that. So we have our node ID, right? So this one is our node ID that we get from the pointer. So we want to check its body. So const body is, I guess we could do self dot so we have node child, but I think we are going to need node sibling of node ID or node index. So node child. And we are also going to need node parent for that matter. So now I'm thinking, do I recreate node index as a type and put all these helpers inside it? We could try that, actually. We could try that. So let's go for, we should have it somewhere here. It should be pretty much the same as this one. And we just put that there. We replace, no, there's nothing to replace actually. We just need to remove this. We need to remove this, I think. And we need to remove max order. Do we need max order though? No. Actually, we just need this. Yeah, sure. So let's go here and do value is whatever we've just copied. Right, so here we are just going to need, I'm just going to replace all of this with a variable that I'll call node index max log. Sure, and I'm just going to get that here as a comp time. Node in, not node, node index max log, and it would be a comp time int. Sure, we don't need that anymore. I guess here we just need to, do we need anything here? No. Let me just do const node index type is, let me just rename this to this, and we can use it everywhere else. So index type, and here we are just going to need a node node index, which would be a node index type, right? And yeah, all of this would go basically, and we just need to do value is node index. Yeah. Okay. We are going to need to compute the parent, and the children and the sibling. But for the children, we already have node child, I think. So we can just basically yank this from here, put this here, and that's sorted. Now, let's think about the sibling. I think we pretty much need to use our XOR trick, because the siblings are one apart. The left one is a power of 2, and the left one is an odd number. Rather, the left one is an even number, and the right one is an odd number. Right, so sibling here, let's try to find this. So we know that the least significant bit here would be 0 for the left child, and for the right child it will be a 1, right? So if we want to go from left to right or right to left, we are going to XOR 1. So if we do that XOR 1, actually let me notate this differently with the real XOR symbol. So if we do that XOR 1, we are going to get a 0 and all the other bits. And if we do that here, we are going to get 1 and all the other bits. So yeah, we just need to XOR it basically. And there's no need to do the minus and plus. And we can get rid of these. So that's it for the sibling. Now for the parent, we know that if we have, so let's go for 2 and 3, their parent would need to be, so here we'd have 1 and 0. These ones go to parent 0, and these two need to go to parent 1. Right, so we basically have them, and we hope that actually there's nothing to hope for. We just divide by 2 and that should do the trick. Yeah, as long as the division rounds down, basically. So let's do so just something like this, basically. Yeah. Yeah, okay, that looks good. So here we are going to, oops, not what I wanted to do, but so this one would need to be node index type of that. Is that right? Yeah, that looks right. Looks about right. Now that I think about this, no, that's fine. That is fine. Okay, but now we are going to have quite a few changes to make in our code for it to start working again. And actually, let me just do that by asking the compiler. What? Surely is a problem there. Oh, of course. That's my bad. We are not using this anywhere in our. So hold on, let me go kernel source, and we should just do zig build test. I think that should give us the errors. Yeah. Okay, so 220, and here we don't have any node child, so that would be node index.child. And we should get rid of this. Actually, that's fine. And this here would be node index dot child, and we can just get rid of that. So 244. Yeah, that's fine. 122. What is the error here? Expect node index found comp time int. Sure. Node index.create with a 0. It's okay. 49. Oops, no, that's just a 125. That would be node index.create with a 0. And let's rebuild this and see. So 246, that's fine. So 24. What's 24 about? Bit shifting operation, expected integer type found body node index type 6. Dot value. Okay. Let's see. Right, so now we are going to go through all of so 64. That would be self.value. Oh, okay. Sure. That needs that. And then this needs self.value dot whatever that is. Okay. And I guess that's fine. And that should be fine. Okay. So 188 or 89. So this one is that dot value, or hold on. No, this one should be like this value is that. And node index, this one needs to be value. And let's see. 276. And of course, here we need to do this dot value. So it needs a type, so we are going to need to give it a type then. Field type. field type of node index, and the field name is value. And of course, we need to close that. That should be fine now. Okay. So 303. Okay, fine. Node index hold on, how did we test the no, that should be okay. Node index node index, and same goes here. Okay, and of course this one, let me just do this. This one would need to be child. And I guess we should also get rid of this. But now it means that we need to actually hold on one second. So let's get this first, go over here, do this. And we should do dot value is this, right? And of course we need to put this between parentheses. And here also. And now we can just paste in whatever we've copied from before. Right. So let's give it a quick build again and see. Still 5 errors. Function expect 2 arguments found 1. What? What is that? 3, 6, 4. Oh, yeah, of course. So alignment would need to be mem alignment dot I guess 1. Sure. Who cares? And I think we are going to need to put pretty much the same thing here and here. And here and here. I feel like we've made life a bit more complicated for ourselves, but we move. Okay, that looks all right. Now we still have a few errors. So in 244, let me just do this, and you know what? There we go. Okay, let's see here. So we found a stringer, a formatter string D for node type. And where is that? It's called here at 343. What? Expect equal. node ID from pointer. Confused. Right. Okay. That's fine. That is fine. So we need to go here, do something like this. Value is that, and then go over here and do. Right. Let's see. So we still have 3 errors, and I guess one of them should be at 343 still. Oh, right, of course. These ones. Value is 0. Okay, let's try again. So we still have this formatter here that's not happy with us, but so let's try to find bucket, those are all buckets. All right, so it should be this one. Okay, let's just see if we've missed something else. No, those are fine. And we have 2 errors, incompatible types, 307. Okay, of course. So this one here expects to be a node ID. Okay, it's fine. Actually, it's probably faster for me to just do this. 2 here. Oops. It's 2, and this one is 5. It is 5. Yeah, that's not 5. Okay, so let's try again. 2 errors still. Where is that? .307. Okay. Not sure what the problem is. So we have 2 incompatible types. So let's go for the other one first. 335. Okay, so I guess it just doesn't resolve the type correctly. So node index. Okay, if that solves that problem, then we know that's the problem, of course. So it's 307. fine. So this one would need to be test body.node index. Okay, our tests should still pass. Actually, I would like to probably go ahead and just remove the debug things just for now. Okay, that's fine. Just to declutter the display a bit. That's fine, and that should be okay. Buffer. There we go. So all tests have passed. Cool. So now let's go back to our free here. Cool. So now we don't need to do this anymore. We've finished our side quest, so this one would need to be sibling, right? Let's go here to node index just so that we know what it is, and let's check for so if self.nodeState is set, and this one here takes so let's see. Okay, so first of all we need to do this. Yeah, now I remember. So we need a bucket and a body node index. No, hold on one second. Actually, we don't need the body node index yet. We can just do fine with our node index. Yeah. So if node state index dot value is set, and of course we need to no, that should be fine. That should be fine. So if it is not set, we just break out of the loop. We should have all the things we need. We did not match any of our siblings, so we have no bodies to recombine, and we are going to just break out of the loop with our current bucket index and node index. Yes. Otherwise, if it's set, yeah, actually no, there's something missing here. There is something missing here. We need to check that its parent is set. So we basically need to do this. Yeah. So if it has a parent and is set the parent of our node, then we break, right? Otherwise I guess here we just return, since we should have reached the highest bucket. Yeah, but no, we still need to just break here. And this one here should be, if it's not set. Otherwise, if it is set, we should go ahead and take the sibling. So const, I guess, body node index. That would be node index dot sibling, and we basically remove that from our free list. So that should be, so we are going to have to iterate our free list for that bucket ID. So let's create an iterator, which would be self.buckets of that bucket. Dot iter, of course, and while iter.next, we capture that as node. Sure, why not? And we need to check if node dot what do we call that item? I think what's node? Doesn't know. So bucket free list has a bucket free list item, and that should have a node index. Cool, very nice. So it's called node index. Should we do dot value, or can we just compare them? I think for now let's just do dot value. So if that is equal to our body node index dot value, then we just basically remove it. We remove it and we break. I guess self dot buckets. Let's let's do this as a defer. So self dot buckets at bucket dot remove, and we need to pass it the node, and that node would be node. Yeah, so that should be okay. That should be okay. So once we do that, we need to go bucket is equal to bucket minus 1. Let's do this. Or rather plus 1, because we are moving towards the higher order buckets, which have larger amounts of memory. Right, and then node index is current node index dot parent. Right, and does this So we probably need to change the check here and do node index dot value is different from no, actually that's fine. But this parent here, this parent call can fail, so we'll probably have some error to handle in a bit. But I will try that. No, actually, let's see. So parent value we divide by 0, and I guess it should error, so we should still need to leave the try there, go there, and let this be, let this propagate the error. Okay, so now that we have this, we go again. We continue the loop until we basically reach the final order, or we reach one that's not split and we can break out. And when we break out of this loop here, what we need to do is basically insert a new block, new free block, into our list. And actually, I'd also want to defer allocator dot destroy. Wait, is this what I think it is? No. Alloc dot destroy node. Yeah. Just so that we don't be leaking anything. Right, so now that we are out of the loop, we are going to go ahead and do self.buckets at whatever bucket we've reached, dot append append, sure. Did we use prepend somewhere else here? Yeah. So actually, let me just get this and go ahead here, do that, and we should be okay. So I'm just going to change this to be that. This would be node. This would be node, and this would be node. Right, except that the node ID here would need to be well, just basically node index. The node index we've gone to. Cool. So just make sure that this is of node index type, that's correct. And that should be it for freeing the memory. Okay, so I guess we just need to write a few tests for this, and we should be all good. Right, so I'm expecting our free test to be fairly identical to our allocation tests, I should say. So, first of all, let's get ourselves set up in a nice case where we would have a bit of fragmentation. Actually, now that I'm reading this, case 4 is not really well labeled. So what are we doing here? We are allocating 8 bytes, then 16, then 2 bytes, then 1 byte. Yeah. So let's copy that up here, and let's get rid of a few cases here. Let's set ourselves up for I'm just going to retain this, get rid of all the other ones, and I am going to change this a bit. So I want a case where I have the 2 buddies. Let me just get rid of all the expects. And actually, let me just also get rid of this. Yeah, sure. I'm gonna do that. Right, so if we just do this and get rid of all of that. So So we are getting rid of this body here. We should also probably get rid of some other body. So let's do something like this twice. And yeah, we'll see. So from here, I'm just going to print the memory layout to see what we have. So we have a, so this one is 128, bucket 7 is 128 bytes, bucket 6 has only the, let's actually draw this. So we have 7 free lists. Need one more. Right, so this one would be 0, this one would be 7, 6, 5, 4, 3, 2. So we do have 8 of them then. Yeah. My bad. I don't know how to count. Right, so this one here is empty. This one here has the later half of, so let's actually draw all of them. So this one here is fully used, just gonna do that. This one here has this first half used, since we only have node index 1 in there, so that's node index 1. This one here, so it should have 4 splits, and all of them are used. No, actually not all of them are used, but these ones are used, right? So this one here, actually I should not have drawn this part here, since it's free in this region here. It should be free in all of them, so I'll skip it. Right, this one has 8 splits. Yeah, I didn't think this through. It's gonna get hard to draw all of them. Okay, that should be fine. So 4, we have node index 3, so that 0, 1, 2, 3. So all of these cells are filled. This one is 3. In 3, 2, we have nothing, and in node index 1, we have just node index 7. So in this one here we have 8 cells, and in this one, all of them are used. Yeah, actually, this is kind of hard to draw. So here we have 13, 7, 3, and 1. So we do have this body here that's used. So we can probably go ahead, and we have also this body here in node 4. So this one is 128. This one is 64, 32, 16, 8, 4, 2, and 1. Right. So if we can just free this section here, these 4 or 8 bytes here. No, these are 16 bytes. So if we can free cell 2, we should see it recombine with its body 3, which is here, and we should see it move up to this bucket here 5 as this cell here. Okay, now we have our plan. Let's do that. So we probably should do this. actually, let me just leave it as case 1, and we'll go from there. I'll also do this down here. I'll mark this alloc, and I'll mark these 3 with the space. Cool. So now that we know what we're doing, we are going to go ahead and get const alloc 8 bytes 1 and const alloc 8 bytes 2. And here we are going to go ahead and do so body.free, and we need to pass it the pointer, so that would be alloc 8 bytes 1 with a size of 8, and of course this needs to be tried, and this one here needs to be 2. Right, so let's see what we get. You cannot assign to constant. Well, that's great. So 264. Sure. Okay, so let's see what happened here. A bit of separation would do us no harm. So let's get this, do that, and just do something like this. Actually, that's fine. Okay, cool. Right, so what has changed here? We have this node here that appeared in node 3, which is, so 3 is 8 bytes, right? And that means that if we free its body, we should see it recombine and move up to node 4, recombine with 3, which is its own body, and then move up to node 5, to bucket 5. Right, so if we now go ahead and free, so I guess we need to free the rest of the allocations. Actually, let's first of all just try to free this one here. So const alloc 16b. So try body.free alloc 16 b with a size of 16. Okay, so what has changed here? So here we can see that we have 1 and 3. And here we can see that we have 5 and 4. Okay, so we do have a problem here, because if we have 5 and 4, we should recombine them, since both of them are free, and they should both belong to the same, basically they are buddies. Okay, so I guess we are going to need to go ahead and add some login somewhere here. So let's do debug.print, and I'm going to print, let's not forget this, and we are going to print found, I guess node at, let's do that, let's do bucket that, and ID is that, and then here be bucket and node index.value. Sure. So now we have that. We are going to check for its parent. Let's do parent state is something like this. And this here would do self dot node state dot is set parent node index dot value. And here I'm just gonna do any, so that's fine. We now should move to this sibling node, let's call it buddy node is, let's call that bucket D and index D, and then this would be just the same bucket, and this would be buddy node index.value. Oops. Okay, so found node at bucket 3 index 4, parent state is false. Oh, yeah, okay, that's fine. I think I've forgotten something that's very important. We never actually flipped the state of this node's parent. So once we insert it, we need to flip the state of its parent. Actually, let me just go ahead and copy that from here. Yeah. So node index, we get its parent and we toggle its parent. It does have one. Okay. Right, so what do we have here now? So what has changed? Now we can see that the parent state is true when we try to free 5. Its buddy node is 4, so we find those. And we recombine them since I don't see 4 and 5 here anymore. Now, the thing that I see is that we have a new node here at bucket 5, which is as we've expected. Here we had 3, and here we had 4 and 5. So we had 4 and 5 combined to 2, 2 and 3 combined to 1, and 1 got promoted up here. Right. Okay, that's pretty cool. So now if we move forward, let's do the same thing here. Let's basically assign all our allocations. So this one would be 3. Let's give it 0. This one would be alloc 2 bytes 0, and this one would be const alloc 2 bytes 1. This one would be const alloc 1 byte 0. And the other ones are okay. Cool. So now if we go ahead and free all of those, alloc 1 byte. Actually, let's do them in order. So 8 bytes 0 with size 8 bytes. And we need 3 more. So let's do that. So we need 2 bytes. So here and here we are going to do that. with this being 2. Wow, okay, cool. And of course, we are going to need to use the correct IDs here. Of course. Right, so 1 byte 1. So this one will need 1 byte. There you go. So with this, what I'm expecting to see is that all our nodes have been freed and we have just one block of memory. And that's not the case. And let's see what the problem is. The problem is we are trying to get node index from pointer. And that failed somewhere. Integer overflow. Okay. So that's at 188. So first of all, let's try to do +1 minus max order, just to see if that's the problem. Usually that's the case. And yeah, that was the case, but now we still have the other problem that we've expected, which is we get to a point where we don't have parents for our node, so this one here, and it just explodes. Right, so here, what are our contingencies for this case? We don't want this to error. We just want this to, if it has no parent, we should probably just break the loop. Yeah. But we should break the loop before increasing the bucket. Actually, it doesn't really matter because we'd still break once we are done with this one. So let's actually do break the loop. Okay, so we still have issues. We still have issues. We are missing a bit of memory though. This one here still has node index 0. And this one here is still missing its body. This one here is still missing its body. So I think this one has caused all the problems below it. So let's see. So let me add something like recombining index D and index D to bucket this one. And this here would need to be, so node index so let's see, this one needs to be before we we do any of the changes. So that would need to be node index and dot value and body node index dot value and bucket +1, I guess. Yeah, okay. So we have first recombination here between 5 and 4 to bucket 4, right? Then we have 2 and 3 to bucket 5, so that's basically actually let's do something here. Let's go down here, and every time we free something, I'm just going to prefix that with a free space, freeing, so 8-byte 1. Sure. And let's do this. And let's go here and do 2. That's 16 bytes. That's 8-byte 0, and that's a 2-byte 1, 2-byte 0, and just 1 byte. Okay. So now we are going to see where it starts to snowball. Right, so here we are freeing our first or our second 8 bytes, and the first one has index 4. This one is its buddy, so it's index 5. We recombine the two, then we move them up to bucket 4. We go to bucket 4, we find 3. We see that 2 is also free, so we recombine those two to bucket 5. Okay. In bucket 5, we have no other buddy to recombine, so we skip, basically. Right, here, so for 16, we free one node at bucket 4 with index 1. Its parent is not free, not split, so we stop there. Here we are freeing 8-byte 0, which would be index 0 in bucket 3. Its parent is not split, so we skip. We free the 2 bytes, so we go from index 5 bucket 1, and that's pretty much it. And then we free the 2 bytes 0, which is index 4 bucket 1. We just free its buddy, so we should recombine them. We are recombining 4 and 5 to bucket 2, except that bucket 2 is not free, or we don't have any free buddy. So now we are freeing the last single byte that we have, which is basically holding up this whole memory from recombining. We have it as index 12 in bucket 0. We have its buddy that's free. We recombine them to bucket 1. In bucket 1, we have so 6. So this one goes to node 6 in bucket 1. Node 6 in bucket 1, or we have node 7 in bucket 1 that's free, so we combine 6 and 7 to bucket 2. In bucket 2, we should see that index 2, which is the parent of 6 and 7, is free. It's index 3 that's the parent of 6 and 7. We find that its buddy, which is index 2, bucket 2, is free, so we recombine those two. And then we, so 2 and 3 have a common parent in bucket 3, which is 1. Right, so this one goes to bucket 3, 1. Its buddy is bucket 3, index 0, so that's free. And we should recombine 1 and 0 to bucket 4. And the parent there should be 0. And its buddy is 1. Okay, that's fine. And we then recombine the newly formed index 0 with index 1 to bucket 5. But that should go to 0, bucket 5. Yeah, so we do have a bit of an issue there. So where did we not find a parent though? I don't see it. So where is the parent missing here? Right, so no parent Sag. Let's keep that in there. And here we want to give our node index. Let's actually copy that. So ni is node index. And this would need to be that. This would need to be ni.value. Sure. Just want to see where we are missing the parent here. Wait. So node 0 has no parent? That cannot be right. So we do have a problem in this logic. Yeah. There's a problem there. That's fine. So in remove bucket node, remove segmentation fault. So we surely did something that's not good. But let's see that at least we are moving forward. So here we have index 0 combined in bucket 5. And then we move from bucket 5 to bucket 6 by combining 0 and 1. And then we go to bucket 6. And we have its body that's at index 1. And we try to remove it. And that's where it all goes down. Okay. And the error is on trying to set the head. Okay. Right. So we do the remove. We so where do we try to set the head? So this here, 202. Yes. And that goes like field head.next. Or rather, we get the linked list item and we set our current head to the next item of our list. And that somehow causes a segmentation fault. Okay, let's do something real quick. Let's just make sure that all our prepends, so we have 2 of those, and we create the nodes for those using our allocator both times. Do we also have some append? Yeah, so we do have an append here. The node we append is also created on the heap. So I don't really see why we have a segmentation fault. Except if, oh, I think I see where the problem is. Defer. There we go. Fixed. At least I hope. There we go. And now we have our full memory recombined. Our free is finally done. Our body allocator is 99.9% feature complete. So can we just plug our free here, give it a test with this. So body allocator, yeah, I'll just move the test, and I will also try alloc dot. So we created that with alloc, so we should use free, I guess. And we pass it slice. And that should not fail, so I should remove that. And I should see no issues, I guess. That's the only thing we can test for. Expected 2, found 1. What? Found 3. Oh, okay. So let's go up here, go there, and we can add alignment, which is the mem alignment, and we can just not use it. That should be okay. Cool. Actually, type void found whatever that is. So let me go up here. Actually, that's not where I want to go. I want to go here, and I want this to just be that. Okay. Error union is ignored. Okay. Sure. So let's go here, undo. Yeah, let's panic. Error while unexpected error while freeing memory from actually we can be smarter than that. Memory. Yeah. So what is the problem there? Oh, right. Yeah, let's forget about this then. Member function expected 3 arguments, found 2. Okay, fine. So we need to go up here and add. Can I just go ahead and copy this? Okay, so let's do something like so. Oops. Yeah. There we go, and we can just keep doing this. Whoopsie. What is going on here? Why is our pointer minus start pointer overflowing? Oh, okay. Okay. So this init, we just set the pointer. And when we try to get the node index from pointer, we use memory.pointer. But we've set memory here. So what is going on? Debug print pointer oops. And this would be pointer there. Okay, so where is my log? Okay. Right, so let me just go ahead and remove all of these. Well, not remove them, just temporarily move them out of the way. Right. Okay. So now we need to go to 184 and we need to set print debug print start pointer is any, and that would be start pointer, of course. And we also need this. Okay, let's see. Start pointer is, what is that? Oh, wow. Nice. Very nice.